redevelopment agency faced several challenges in regards to bringing the Terminal 1 site forward for productive reuse. The first challenge was the cleanup methodology that we would use for the site. Once we established that the site had some serious contamination left by the previous tenants, the redevelopment agency, working with Geomatrix, our environmental consultant, looked at what methodology would be used on the site in regards to cleaning it up. The more traditional dig and haul method was looked at. A price was associated with that of approximately $7.5 million. We also looked at a more innovative approach, which was the in situ treatment. This treatment methodology would deal with the contamination on site and had a price tag associated with it of about half the cost for the dig and haul methodology. The redevelopment agency, working with Geomatrix, Regional Water Quality Control Board, held a number of community meetings where we also received input from the community in regards to the cleanup method we were using and giving them information in regards to the in situ treatment. Geomatrix went out and then, working with the redevelopment agency and Regional Water Quality Control Board, hired TerraTherm, the environmental consultant, who would be actually instituting the cleanup methodology that's being placed on the site.
This is a very exciting project. Richmond is redeveloping a former industrial area into what's going to be a brand new housing project. So this site was a former tank farm, which contained lots of different types of chemicals, petroleum products, solvents, and some foodstuffs. But as an industrial project, it's somewhat impaired, and that has to be remediated. So Geomatrix Consultants, the company I work for, is the consultant to the Richmond Redevelopment Agency, and what you see at the site today is a culmination of maybe 4 or 5 years hard work to clean the site up. And the first step is that you do some investigation work, and that means taking soil samples and water samples. You send those samples to the laboratory, get the chemical data back, and then you decide what areas of the site are affected. Those data are presented in a report that goes to the public, and then the next stage is, once you've determined where there is contamination, you then look at all the different alternatives that might be used to clean up the site. We looked at many different types of technologies and alternatives, but at the end of the day, the main contenders were either to dig it up and take the contaminated soil to a landfill, or to do some kind of in situ treatment. In situ means treating the material in place, in comparison with excavation, where you would dig it up and essentially just move the problem somewhere else. At the end of this, Richmond is going to have a beautiful site with brand new housing with fantastic views.
TerraTherm's technology is called in situ thermal desorption, commonly called ISTD, and it's a proprietary technology that was developed by Shell Oil Company back in the late 80s and early 90s, growing out of their efforts to enhance oil recovery. So we started out doing remediation of various kinds of sites, and over time began to get more involved in remediation of chlorinated solvents types of sites, and that's what Richmond is. We completed a project in clay soil, similar kinds of contaminants in Ohio the year before last, and that demonstrated the technology could be used for a site like Richmond. I and my colleagues are based in Fitchburg, Massachusetts. We also have an office in Keene, California, which is east of Bakersfield, and 2 other projects right now operating in California. One's in Alhambra for Southern California Edison. There we're treating a different class of contaminants from those at Richmond. They're PAHs and dioxin primarily, and have met the goals there for the first half of the project and are nearly done with the second half. It's a much larger project than Richmond, and it's taken us a couple of years. We're also doing a project in Carson, which is like this one for chlorinated solvents. That one is being overseen by the Department of Toxic Substances Control, and is also nearly done. So now turning our attention to Richmond, we were selected to design and implement ISTD at this project based on a competitive bid process. They recognized that our technology was particularly well suited to this site. So we probably have the only in situ method of treatment that would possibly work at this site. We began by designing the project using computer simulations to determine what the appropriate spacing of the wells in the thermal well field would have to be in order to achieve the target temperatures within a desirable time frame. What we have at this site is a spacing of thermal wells at 12 foot in a triangular pattern. Altogether there's 138 thermal wells. They're vertical wells. They're installed to a depth of 20 feet. The heating elements that are inside these wells are electric heaters, very similar to the heaters that you'd have in an electric stovetop or a toaster oven. Electric current passes through the heating element and causes the heating element to heat up. In this case, we can heat these heating elements up to as much as 1,500 degrees Fahrenheit. You can turn them up or down as you need to, and the goal in treating the soil is to get the soil up to about the boiling point of water, because at that temperature the chlorinated solvents will be steam distilled out of the clay, and then the vapors can be captured. In the well field, we also have not just thermal wells with heating elements in them, but other thermal wells that also have screens in the subsurface so that we can exert a vacuum on those wells and pull vapors that we're generating from the heating process up into above ground piping and convey it to the air quality control system. These are called heater vacuum wells. Compared to the heater-only wells, there's 126 heater-only wells. There's only 12 heater vacuum wells at this site. We placed a light aggregate concrete cover over the entire treatment zone, and the purpose of that is to ensure that there aren't any fugitive emissions, so that the entire subsurface zone that's being heated is under a vacuum, particularly along its boundaries, and therefore as it heats up and the steam gets generated, the vapors that are created that are contaminant vapors all get pulled into the heater vacuum wells and conveyed into the above ground treatment system. I would also add that we installed a number of thermocouples, which are simply thermometers that measure the temperature at various locations and various depths so that we can track how heating is progressing. The method of heating that we're using is called thermal conduction heating. And with thermal conduction heating, one of the most powerful things, and as a soil physicist, one of the things that appealed to me most about this method of heating is that it relies upon the thermal conductivity of the soil, which varies only by a factor of about 4 across a wide range of soil types. Once the vapors are generated by the heating, and particularly as the soil gets hotter and closer to the boiling point of water, you start to generate a lot of steam, and our treatment process is pulling the steam and the contaminant vapors with it out into the above ground manifold piping, which you can see consists of fiberglass piping that gets gradually larger and larger in diameter the closer you get to the treatment equipment. As the vapors get conveyed into the beginning of the treatment equipment, we have some instruments that measure flow, temperature, and pressure, and that send the signals to the computer in the control room where it's automatically monitored. Once the vapors arrive at the air quality control system, the first thing that happens is that they're cooled down in a heat exchanger. We then convey that liquid water, we call condensate, into a liquid treatment system. This treatment system has several small diameter vessels. There's an organoclay vessel for removing hydrocarbons, and then 2 serial vessels of activated, liquid phase activated carbon. And these polish the contaminants out of the water so that it then can be discharged into the local sanitary sewers. Meanwhile, on the vapor treatment side, the vapors that have been cooled to about 90 degrees C are then heated again in 2 duct heaters. The relative humidity is dropped to below 50% so that vapor phase granular activated carbon can do a good job of polishing the vapors. So once we've dropped the relative humidity, the vapors pass through these 2 vessels and then into our blower trailer. There's then yet another vessel that contains granular activated carbon that's been impregnated with something called potassium permanganate. It's an oxidant. The reason for that last vessel is that vinyl chloride is a contaminant that, although it's present in relatively small concentrations at this site, it's one of the more toxic compounds, and it isn't readily adsorbed to activated carbon, but it is readily oxidized by the permanganate. So we remove it in that last vessel. Then the vapors are pulled through the blower. There's 2 very large fans. One of them is a backup. The other one is turning and creating the vacuum that's drawing all these vapors through the system. The significant thing about putting it at the back end, right before the stack, is that it means that all of the system upstream of that point is under a vacuum, so that if there were any minute leaks in any of the piping, the leaks would be in rather than out. So finally, after passing through the blowers, the vapors are discharged through a stack. The system is powered by power that comes from PG&E's grid. It comes into some a large transformer and some large electrical breakers and switchgear, and is then distributed by the large diameter cables that look much like the cables you've seen at fairgrounds. They're heavy-duty cables. They can carry a large amount of voltage. The actual amount of power that's sent to each location is controllable by some SCRs. Those are silicon control rectifiers, and they're operated by Wattlow controllers that we can turn up or down, much like you can on an electric oven. So you can set the temperature of the various circuits in the ground for whatever you want them to be. And next to that, you can see that the thermocouple boards where we can read the temperatures that are being measured throughout the well field at various locations.
At the end of the process, we have to prove to the Water Board, who is the regulatory agency for this process, that we have met the cleanup standards. So during the feasibility study, we establish concentrations in the soil that we have to meet in order for the site to be declared clean. We take soil cores, we take the cores and send them to the laboratory. The laboratory takes data, and when we get those data back, we compare them to the cleanup standards. It's been very challenging technically, and this is the kind of project that makes people want to be an engineer.
The Regional Water Quality Control Board, working with the community and the Richmond Community Redevelopment Agency, has established cleanup levels for the Terminal 1 property. Geomatrix and TerraTherm have completed over 60 soil samples, and those samples have concluded that the cleanup methodology being brought forward by TerraTherm is below the cleanup levels that have been established by the Regional Water Quality Control Board. The Redevelopment Agency will receive a letter from the Regional Water Quality Control Board stating that the site has been remediated. At that point, the redevelopment agency will then move forward with the redevelopment of the Terminal 1 property.